In this video, we're going to look at the binomial theorem. In particular, we're going to use the binomial theorem to expand out a binomial polynomial. And we'll also use the binomial theorem to find a specific term of a polynomial. Before we do that, though, we want to just spend a few moments to remind ourselves about a factorial. Now, what a factorial is an operation just like natural log and cosine and sine, where the way that we defined in factorial is being, so like 3 factorial would be 3 and then 3 minus 1, which is 2, and 3 minus 2, which is 1, all the way down to we get to 1. This, of course, works for n is greater than or equal to 1. A couple of definitions. 0 factorial is 1, and 1 factorial is also 1. If we're asked to simplify using factorials, of course, I could go ahead and write this out as 10 multiplied by 9, 8, 7, 6, 5, 4, 3, 2, and 1 in the numerator, and 7, 6, 5, 4, 3, 2, and 1 in the denominator. Then I can just start doing the cancellations. Now this is a lot more work than I want to do. I want to make this simpler. So to make it simpler, realizing I have a 7 factorial in the denominator, I can write 10 factorial as 10 multiplied by 9 multiplied by 8 multiplied by 7 factorial. And in the denominator, I'm going to just get 7 factorial. This will allow me to cancel those two 7 factorials, and I don't have to write it out completely. It's not wrong to, right? And then do the cancellation. It's not wrong to, but it does make it a little bit easier. And then what I have left over that did not cancel is 10 multiplied by 9 multiplied by 8. This just gives me 90 times 8, which is 720. 9 factorial, I'm going to cancel down till I get to a 4 factorial, and then I'm going to do that cancellation. So I'm going to take 9 multiplied by 8 multiplied by 7, 6, 5, and then 4 factorial. The reason I stop at 4 factorial is because the denominator has a 4 factorial. So 4 factorial. Now I'm going to have to write out 3 factorial because I won't have a 3 factorial in the cancellation in the numerator. So I'm going to have 3 times 2 times 1. And then I'm going to do my 2 factorial, which is 2 multiplied by 1. My 4 factorials will cancel. 3 times 2 is 6, so that gets rid of that. It cancels out. And then 1 times 1 is not going to do much, and 1 times 2 is just going to give me 2. So I can cancel this 2 with that 8 giving me 4. So what I'm really left over with is 9 multiplied by 4 multiplied by 7 multiplied by 5. And then what it is just a matter of getting my calculator out, and I'm going to do 4 times 5, which is the 20, so I don't have to do that part of the calculator. And then I'm going to do 9 times 7 in my calculator, and what I'm going to get when I get done is 1,260. Now C is something that's really important later in calculus 2 in particular, when we start looking at convergence and power series and all of that stuff. So let's spend a few moments talking about that. The numerator is going to be n plus 1, n plus 1 minus 1, n plus 1 minus 2, and it's going to continue down until I get the 2 multiplied by the 1. In the denominator, I have n factorial. Now, the reason I only wrote it as n factorial, this term right here, if I do n plus 1, that's like 3, minus 1 would have been 2. N plus 1 minus 1, this part is n factorial, which means I'm not going to write out all of these other terms. And the reason I'm not going to write out all these other terms is because, remember, if this would have been, say, 10 factorial over 7 factorial, I would get down to a 7 factorial, so I can cancel those out. And then I just get n plus 1 as my final answer. And that's it. Now, we needed to do that because part of the definition of the binomial theorem uses binomial coefficients. So this notation is a choose. So n choose r. You're going to see this if you're in statistics and probability. You would, in your statistics class, you would explore a little bit about probability. We don't do that in this class, but we do use some of the same kind of concepts, which is the n choose r. So if you see it in this form, or you see it in this form, or your calculator may be in this form, and choose R in that form. All of those mean that you're going to take this number n, and it'll be n factorial, this number r, and it'll be r factorial, and then also in the denominator is going to be n minus r factorial. So that is how we're going to define the binomial coefficient, of course, when our n is greater than or equal to r. And it will come clear in a moment. Another little thing that we get is if n and j are both natural numbers, that's what this means, is that n and j both come from the natural numbers, and n is larger than or equal to j, then if I have n choose j minus 1 plus n choose j, I end up with n plus 1 choose j. The proof is in your book for your viewing pleasure, but that's just a little bit of information we may or may not want to ever use. If I'm asked to simplify 8 choose 3, now by definition this means that is my numerator is going to be 8 factorial. That's the number on the top of those parentheses. 3 factorial, that comes from the number in the bottom part of those parentheses. And then it's going to be 8 minus 3 factorial. So once I did as I did before where I had 10 over 7, is I'm going to take this 8 factorial and I'm going to write it down to this. So I'm going to write it down to 5 factorial. So I have a cancellation. So I'm going to write the 8 factorial as 8 multiplied by 7 multiplied by 6 multiplied by 5 factorial. I still have the 3 factorial. I have the 5 factorial. These 5 factorials will cancel. Now, since I know the 3 factorial won't cancel, I'm going to go ahead and expand out the 3 factorial, which we know happens to be 3 multiplied by 2 multiplied by 1. The 3 times 2 is the 6, so these will cancel. So I'm left with just 8 multiplied by 7 over 1. So in other words, I get 56. All right. Now I have 117 choose 0. Well, again, my larger number, not the larger number, the number in the top part of the parentheses will go in the numerator. So this is going to equal to 117 factorial. And I'm going to have 0 factorial, because that is the number in the bottom part of the parentheses. That's this number will go in the denominator. And then it's going to be 117 minus 0 factorial. Well, one of the definitions that we have from up above is we know that 0 factorial is equal to 1. 117 minus 0 is 117. So I have 117 factorial over 117 factorial, which is just 1. Looking at my last example here, this is one in which I have no idea what my number n is. I just happen to know it's bigger or equal to 2. So again, this number is in the top part of the parentheses, so it goes into our numerator, so n factorial. And then I'm going to have n minus 2 factorial, because this is the number in the bottom part of the parentheses, so we know that goes in the denominator. And then also in the denominator, we're going to get our larger number, which is the number in the top part of the parentheses, so n minus 2 factorial. And before I clean this up, or before I start expanding out, I know that this is going to be n minus 2, or plus 2, so this just ends up becoming 2 factorial. So my numerator, n factorial, n minus 2 factorial, and then 2 factorial. This is similar to saying if I have n factorial over n minus 2 factorial, this is similar to saying I have 8 factorial and then 2 minus that, which is 6 factorial. Now, if I had numeric values, I would write this as 8 multiplied by 7 multiplied by 6 factorial over 6 factorial. And I would cancel these out. I'm going to do something similar here. I'm going to have my first term, which is like the 8. N minus 1, that's like the 7. N minus 2, that's like the 6 factorial, over the n minus 2 factorial, and then 2 factorial is just 2, because it's 2 multiplied by 1. That allows me to cancel out that n minus 2, leaving me just n minus 1 all over 2. So that is the answer. My answer will be in terms of n and not just a numeric value. Now, we needed all of that stuff because here how we are going to define the binomial theorem. So we have these two terms, which makes it binomial. We have this n, where we assume n is going to be, because we're using series here, we're assuming n is a natural number. K equals 0 to n. K is my dummy variable. N is, notice how this n, so squared, this would be a 2. N choose k, and then it's going to be x to the n minus k, y to the k. Notice my very first term is n to the, or x to the n. N choose 1, n minus 1 times y. N choose 2, n x to the n minus 2, y squared, all the way down to, I get to the n minus 1, n choose n minus 1, x to the n, x times y to the n minus 1, and then just y to the n. So what you might see in other textbooks is they actually expand it out just a little bit more, and they say, wait a minute, we're going to choose n choose 0, x to the n, y to the 0. So they actually use that as the first term. It's not a bad idea to think about that as being the first term. And when we're looking at this structurally, n choose 2, x, this should be x to the n minus 2, y to the 2, and then dot, 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 dot. My second to last term is n minus 1, so n choose n minus 1, x to the 1, and I want to write that as y to the 1, and then I have y to the n minus 1, and then my last one is n choose n. So I actually like this definition a little bit better. N choose n, x to the 0, and y to the n. And the reason I like this one a little bit better is that you can see the progression where this 0 matches with this 0, and then we get all the way down to where choosing n choose n. So n choose 0 ends up becoming 1, and that's why you don't see it here, because it is 1. N choose n is also 1. So again, that's why you don't see that there. But for consistency purposes, I really like to start out with 0, 1, 2, all the way up to n minus 1, and then n in my choosing. So n choose all the way from 0 to n. So n choose 0 being my first one, and n choose n being my last one. I also like to write y to the 0 on my first term, even though I know it's going to be 1. Just like here, I like to write this as x to the 0, even though I know it's going to be 1. Simply because then I can see the progression in the exponents. So n, subtract it, you drop an exponent, you keep dropping an exponent all the way down until you get down to an exponent of 1 and then an exponent of 0. Similarly, on my y's, my exponent of 0, then my exponent of 1 on the y, then the squared, then to the n minus 1, and then finally to the n. Now here's a little thing that will help you out. Notice that this choose is the power on the second term in the binomial expansion. This choose is this power, this choose is this power. That's why I like to have this choose, so that power. So you can see that connection. And if I want to go to a specific term, I want to have that connection. That's going to help me with that connection. Also, another thing to note is notice that if you were to add these exponents, which of course you're not because the bases are not the same, if you were to add those exponents numerically add up to whatever n is. N plus 0 is n. N minus 1 plus 1 is n. N minus 2 plus 2 is n. 1 plus n minus 1 is n. 0 plus n is n. So it's just structurally, I just like to see it using this formula. This one is totally fine. There's nothing wrong with it. I just prefer this other one so I can make those connections. Now, when you're doing the choose, so this piece right here is the coefficient. That's why we introduced it as the binomial expansion coefficient. It is the coefficient multiplier. Another way that we can find this coefficient multiplier is Pascal's triangle. You might have seen or heard of Pascal's triangle. So if we are doing x plus y to the 1, we know this is just going to be x plus y. The exponent here is 1. See how that's 1? 1 plus 1 is 2 terms. X plus y squared, when it gets simplified, the exponent is 2. 2 plus 1 gives me 3 terms. Notice I have 3 terms. So this is also a way to help you determine how many terms you're going to get. So x to the third, exponent is 3, 3 plus 1 is 4, I expect 4 terms when I get done simplifying. 4, I expect 5 terms. Notice how the exponent is in, pattern is in plus 1, and in general the number of terms is going to be your power plus 1. Again, notice these exponents, and that was what I was talking about here. So what they're calling out here is the exponents. Again, you really can't add the exponents, right? You really can't add them. You really can't say 4 plus 0 because the bases are not the same. However, if you're trying to do some housekeeping, you can say, but wait a minute, my exponents do need to add up to 4 or whatever my n is. Notice how x goes down. My first term goes down in exponents as my second term goes up in exponents. Now, if we look at Pascal's triangle, let me go ahead and lock the rotation again. I don't know why it does that sometime on me. So if we look at Pascal's triangle, we can determine the coefficient multiplier by using Pascal's triangle. This first one, this one here, is when I have x plus y to the 0. Provided x and y are not in any weird kind of divisions or anything, this is always just going to be 1. This second row where I have 1 and 1, this is x plus y raised to the 1, which is just x plus y. This third term is the x plus y, or this third row, excuse me, is x plus y squared. This becomes x squared plus 2xy plus y squared. Notice how my exponents on the x's go from 2 to 1, and there really is x to the 0 there, but we don't write it. Similarly, there is a y to the 0 here, so my y powers are going from 0, 1, and 2. Notice this 2 is this 2. These are coefficient multipliers. This is x plus y raised to the third power. So what I really have when I expand this out is I'm going to have y to the 0, x to the third. In fact, I'm going to write it as x to the third first. X to the third, y to the 0. My coefficient multiplier in my second term is 3. So 3. X choose 2 because I'm going down a power. Y choose 1 because y is going up a power. Coefficient multiplier. So plus 3, x dropping a power from 2 now to 1, y gaining a power from 1 to 2. And then my last one, this is a 1, this is a coefficient multiplier, so it is 1, just like there's a 1 here, 1 multiplied by x to the 0, which is 1, and y to the third. X goes from cubed, squared, linear, 0. Y goes from 0, linear, squared, cubed. Notice that these two numbers, numerically, of course we're not actually adding exponents, ends up becoming the 3. Now, where this comes from is going back to the 3 choose 0. So where that 1 comes from is 3 choose 0. This is 3 factorial over 0 factorial, 3 minus 0 factorial, which ends up being 3 factorial over 3 factorial, which is 1. This one comes from n, so n choose n, so it's 3 choose 3, which ends up becoming 3 factorial over 3 factorial, 3 minus 3 factorial, which is 3 factorial, 3 factorial, 0 factorial. In other words, it's just 1. This 3 comes from 3 choose 1, because remember it's my second term, so I'm doing 3 choose 1. This is 3 factorial, 1 factorial, 3 minus 1 factorial. So 3 factorial, 1 factorial is 1, so 2 factorial, 3 multiplied by 2 multiplied by 1, 2 multiplied by 1. There is my coefficient. So I can find my coefficient multiplier, and make it very clear. It's a coefficient multiplier. It is not just the coefficient. It is just the coefficient if the coefficient on your binomials are just 1s, but if those coefficients on your binomial terms are not just 1, it is not just 3. It is a multiplier. Similarly, we can get the same value for that one too using the definition. Now, we're going to expand out, and we're going to use the binomial theorem, or we can use Pascal's. I'm going to use the binomial theorem on the first one, but I'm going to use Pascal's on the second one because it's here. The fourth row. Well, actually, it's the row that has a 4 in it. Ooh, before I do that, though, I'm going to talk a little bit about how Pascal's triangle is built. Notice, to build Pascal's triangle, there are 1s on the outsides, on both outside of the triangle, like the sides of the triangles are 1. And notice on the second row diagonally here, it goes 1, 2, 3, 4, 5, 6. Just like this goes 1, 2, 3, 4, 5, 6. Okay? And that number, 1, 2, 3, 4, 5, 6, is also going to help me to decide which row to choose. So if I want to do this one, x to the 4th, I'm going to use the row that has the 4 in the second position in that row. So that's the one I'm going to use. I'm not going to do that one yet. I'm going to, just a minute. Now, to get these numbers, I add the 2 that are diagonally above. So 1 plus 2 is 3. 3 plus 3 is 6. 4 plus 6 is 10. My next row would be a 1, a 6. These two would come together and give me 15. These two would come together and give me 20. These two come together and give me 15. And these two numbers would give me that 6 and then that 1. Those would be my coefficient multipliers. Now, Pascal's triangle is awesome as long as you're looking at numbers that aren't, or your binomial theorem is not expanding out to really, really large ones. If it's expanding out, you probably want to use the binomial theorem because building Pascal's triangle, unless you're really neat and tidy, and looking at my notes, you know I'm not, that it's really easy to mess that up. So I'm going to use the binomial theorem. This is going to be equal to 5 choose 0, x to the power of 5, 2 to the 0. Now, I don't have to put that one. It is 0. Plus 5 choose 1, x is going to drop a power, so that's going to be x to the 4th. 2 is going to raise a power of 1. Plus 5 choose 2, x is going to drop a power, so it's now x to the 3rd, and its 2 is going to raise a power, so that's squared. I'm just going to erase this, get that out of the way. My next term is plus 5 choose 3. X is going to drop a power, so this is 4. And then 2, or excuse me, that didn't drop, did it? That's like the opposite of dropping, that's going up. So this is going to be squared, and it's going to be x to the 3rd. 5 choose 4, I'm almost to the end. X to the 1, 2 to the 4th, and then my last term is going to be 5 choose 5. X to the 0, again, don't need to have that, 2 to the 5th, 2 to the 5th. Okay. Now, 5 choose 0, we know this is equal to 1. 5 choose 1, this is equal to 5. So those are the two that are easy. 5 choose 5 is equal to 1. 5 choose 4 is equal to 1. So that's pretty much, if you have any number choose 0, it is 1. If you have any number choose 1, it is that number. If you have any number choose 0, it's 1. If you any number choose itself, it's 1. If you have any number choose 1, it's that number. Any number choose 1 less than the number you start out with, it's 1. So those are the easy ones. These are the two that may take a little bit of time. And so 5 choose 2 is going to be 5 factorial, 2 factorial, 5 minus 2, which is 3 factorial. Now, if I were to do 5 choose 3, it's the same thing because it ends up being 3 factorial minus, or 3 factorial times 2 factorial in the denominator. So that's kind of nice. I can also go up here and say, okay, the 5th power, that means these are my coefficient multipliers. Notice that this 5 aligns to this 5. This 1 aligns to this 1. This, and I had 1, and this should be 5 here. Bam, that's 5. 5, nope, come on, here we go. This is 5. Notice this 5 aligns to this 5. This 1 aligns to this 1. That means without doing any work, this must be equal to 10. This 10 and this 10. So that tells me the coefficient multipliers are 10. Now, I say multipliers because that is not just the coefficient. That's not the coefficient on those terms. It is the coefficient multiplier. So now let's go ahead and write this out. So I have 1, I don't know why this is taking so long. I have 1 multiplied by x to the 5th, and 2 to the 0 is just 1, so that's going to be times 1, plus 5x to the 4th multiplied by 2, plus 10x to the 3rd multiplied by 2 squared, plus 10x squared multiplied by 2 to the 3rd, plus 5x to the 1 multiplied by 2 to the 4th, and then lastly 1 multiplied by x to the 0, which is just 1. So I can write that 1 times 2 to the 5th. I'm not done yet. The reason I'm not done yet is I have to do this coefficient multiplier by that number, right? Because it's plus 2. So it's going to be x to the 5th plus 10x to the 4th. That's because of coefficient multiplier and 2 raised to the 1. Plus, this is going to be 40. 40x to the 3rd. That's because I have this 10 and 2 squared, which gives me 40. So it's that choosing is a coefficient multiplier. It is not the coefficient. Then I'm going to have plus, I have 8 times 2 to the 3rd, which is 80 x squared. It's because of that 10 and 8, and the 2 raised to the 3rd power. And then plus, I'm going to have 5. 2 raised to the 4th power is 16. So 5 times 16 is, let me check, is again 80x. And that's because I have the 5 multiplied by 2 raised to the 4th power. It gives me 80. And then I'm going to have plus, and then 2 to the 5th is just 32. So x plus 2 raised to the 5th power is equal to this polynomial right here. So don't forget, if I'm using Pascal's triangle, or if I'm using the definition, those numbers that I'm getting when I do the choose are the coefficient multipliers. It is not necessarily the coefficient. And you're like, but wait a minute, on my last example it was. Well, it was, because I had coefficients on the x and y to 1. The coefficients were 1. Now, if I expand this one out, because the coefficient on this is 1 and the coefficient on this is 1, when I expand this out, using Pascal's triangle, I'm going to have x to the 5th, y to the 0. I don't necessarily have to do the y to 0, so I'm not going to this time. Plus 5, because that's this 5 right here. X 1 power less, y is now introduced. The power of 1 plus 10, because that's this one. X to 1 power less, y is going to increase a power, plus 10, and that's this one. X to the power less, y increasing a power, 5. X dropping a power, y increasing a power, and then lastly, y raised to the 5th power. That's because my coefficient on x and y are both 1s. This had a number 2. It was not a 1. It was not a variable. It was the number 2. So here, where I have a variable of y with a coefficient of 1, everywhere I see in this y, because it's a y, I'm going to have to do the same thing with the 2 because it's plus 2, so numerically. So here's what it looks like when my coefficients are both 1, I have variables. Here's what it looks like when I have a coefficient of 1 on the x, but a numeric value for, quote, the y part. All right. Now, nice little side note. Let's go ahead and do another example. Come over here. I'm going to come over. I unlocked again. Just a minute. I hate it when it unlocks. Bam. Okay. I can't stand, if you're in my classes, you know I can't stand crookedness. I can't stand crookedness. Okay. Now, let's take a look at the second example here. With the second example, I am going to use the binomial theorem. or excuse me, I'm going to use Pascal's triangle. So I look for Pascal's triangle and I say, wait, this power of 4, so I need this row right here. These are my coefficient multipliers. Those are not necessarily my coefficients. So this is going to be 1 multiplied by 2x to the 4th, negative 1 to the 0. Again, I don't have to put to the 0, but I like to. And then I have a coefficient multiplier of 4. So that's a 4, not a negative. That is just a 4. That looks like a negative. It is 4. 2x raised to 1 power less, so to the 3rd power, negative 1 to the 1 power. There's my 1, there's my 4. Plus 6, that's where the 6 is coming in, 2x squared, negative 1 squared. My 2 x's are going down in power. My negative 1s are going up in power. I'm just going to erase this. And then plus... So plus this 4, it's my coefficient multiplier 4, 2x to the 1, negative 1 to the 3rd, and lastly plus 1, 2x to the 0, negative 1 to the 4th power. Now let's go back and clean this up. This is equal to 1, so I don't really need to worry about that. This is equal to 1, so I don't really need to worry about that. So I have 2x to the 4th. And this is 2 to the 4th and x to the 4th. That power of 4 needs to distribute on the 2 and onto that 4. So this is going to give me 16x to the 4th. Similarly, this is going to be 2 to the 3rd, which is 8 multiplied by 4. So that's going to be plus 32x to the 3rd multiplied by a negative 1. Oh, since I'm multiplying by a negative 1, to the 1 power, that's going to make it a negative 32x to the 3rd. I have 6 multiplied by 2 squared, which is 4, so that gives me 24. Negative 1 squared is just a positive 1, so we don't have to worry about that, so it's going to be plus 24x squared. I have the 4 multiplied by 2, that gives me 8, multiplied by negative 1 to the 3rd gives me a negative 8. So negative 8x, because it's x raised to the 1. My last term, 1 multiplied by 1, multiplied by negative 1 raised to the 4th power, which is plus 1. So here, make sure that you are dealing with your negative exponents correctly. That, or your not negative exponents, your negative 1 to the correct exponents. The other thing is that you've got to make sure that you do this. You take that 2x to the 4th and make sure that 2 gets that exponent of 4 as well as the x. Or otherwise, if you tell me that 2x to the 4th is 2x to the 4th, you're missing the fact that you have to use this ab raised to the n power is a to the n, b to the n. So that power needs to distribute over multiplication on both the a and that b. So make note of that. If you're getting stuff wrong, it's probably because you forgot to distribute correctly on the exponent. All right, now let's take a look at my next example. Now my next example is going to bring in some of your pre-calculus too, because I'm using I. Once again, I'm going to use the Pascal's triangle because it's right here. I might as well use it. It's there. It's nice. It's not bad to use. So this is going to be 1 raised to the 4th power, my coefficient multiplier of 1, 2i raised to the 0. Again, I don't need that. I like to write it. Plus, actually I'm using this row, so I'm going to make sure I'm on the right row. And then I'm going to have plus coefficient multiplier 4 multiplied by 1 raised to the 3, 2i raised to the 1. Plus, now my next term is going to have a coefficient multiplier of 6. So 6 multiplied by 1 squared, 2i squared. My next one is going to be plus 4, 1 raised to the 1, 2i raised to the 3. And then my last term is going to be 1 multiplied by 1 to the 0, 2i to the 4th. All right, now remember, this is going to be 1, just like this is going to be 1, so that's nice. So my first term is just going to be 1 times 1 to the 4th, which is just 1. Here I have 4 multiplied by 1. This is 2 to the 1, I to the 1. So I'm going to have 4 multiplied by 2, which is 8. So plus 8i. All right. This is 2 squared, I squared. Now 2 squared is 4, I squared is negative 1, so this is negative 4. So this portion is negative 4. I need to multiply it by 6 and then multiply it by 1 squared, and so I'm going to get minus 24. All right, this is 2 to the 3rd, I to the 3rd, which is 8. I to the 3rd is negative I. So if you're like, I don't remember this, go ahead and look this up in the textbook, Complex Numbers. I believe it's in chapter 3, maybe chapter 2, but chapter 3. And I know that if you were in my class, we talked about this in our Pre-Calculus 1 class. We talked about the powers of I. So that portion is going to be negative 8i multiplied by this 4, multiplied by this 1 is going to give me negative 32i. Lastly, I have this last one right here. This is 2 to the 4th, I to the 4th. 2 to the 4th is 16, I to the 4th is 1, so plus 16. I need to combine up all of my real parts. So I need to combine up negative 24 and positive 16. Because this is a complex number, I need to write the real part plus the complex part. So 1 plus 16 minus that 24 gives me negative 7. That's my real part. My complex part is the 8i and then minus 32i, which gives me negative 24i. This is my final answer. And you're like, but wait a minute. You told me before, if I have a power of 4, I expect to have 5 terms. And we did. Here's all 5 terms before we cleaned it up. Now this one, because of complex numbers, the way they work, we do need to clean it up as a single complex number. So yes, I did have 5 terms, but when I simplified, it really just ended up with 2 terms. Okay, I will let you do D on your, yeah, no, I'm not. I'm going to do D. I wasn't going to, but I want to now because of the square root, and I need to pay attention to that. So I'm going to rewrite this as negative 1 plus 3 raised to the 1/2, and then I raised to the 3rd power. The reason I'm going to do that is because it's going to help me down here with this B1 when I'm chasing a particular term. Okay. I'm going to use Pascal's triangle again. I'm going to use this row in Pascal's triangle, so it's going to be negative 1 raised to the 3rd power, 3 raised to the 1/2, I raised to the 0, or 3 raised to the 1/2 times I to the 0, multiplied by 1. And then it's going to be 3, that's my coefficient multiplier, that's this number, 3 negative 1 squared, 3 raised to the 1/2, I raised to the 1 power, I'm going up in powers, plus coefficient multiplier up here again in Pascal's, or by the binomial theorem, is 3 negative 1 raised to the 1, 3 raised to the 1/2, I squared, and then my last one is going to be 1 as my coefficient multiplier, negative 1 to the 0, 3 raised to the 1/2, I, and then it's going to be cubed. Now, we know that, again, this is equal to 1, and these two combined, doesn't matter, is equal to 1. So anything raised to the 0 power except for 0 is 1. Negative 1 cubed happens to be negative 1, and then I'm going to have plus, this is going to be a positive 1. I have 3 and 3 raised to the 1/2. So I have 3 multiplied by 3 raised to the 1/2. Bases are the same, so it's going to be 3 raised to the 3/2. Then I have the I raised to the 1. So this is going to be 3 raised to the 3/2 multiplied by that I. This is going to be negative 3. this is going to be 3 raised to the 2 over 2 I squared. 3 raised to the 2 over 2 is just 3, so this is going to be negative 3 multiplied by 3. I squared happens to be negative 1. So this term is going to end up becoming minus 9. My last term, I have 3 raised to the 3 over 2, power to power rule, I to the third. So this is 3 raised to the 3 over 2 minus I, because I to the third is minus I. So this is minus 3 raised to the 3 over 2 I. These terms cancel out. These terms add together. My final answer is just negative 10. So that was actually kind of cool. It's a negative 10 when I got totally done. Okay, now the last part of this section is finding specific terms. Finding specific terms. Now clearly, I am disinclined to, let me just finish erasing this. I am so disinclined to try to get the Pascal's triangle for this first one. There's no way I'm going to write 118 lines. I'm not going to do it. But remember with the binomial theorem, right? When we start out with the n choose 0, x raised to the n, y raised to the 0. Remember when I had x plus y raised to the n. Notice how this matches this. My next term was n choose 1 in x raised to the n minus 1, y raised to the 1. Notice how when I do n choose 1, I have dropped a power, right? I have dropped a power. N choose 1, I have dropped 1 power. 117, that is 1 power less than 118, so I only need to find that second term. And I'm clearly not going to write Pascal's triangle. So I'm going to use this because they want that term containing the 117. The term they want is that 117. So this is the term that I want, because if I have 118 choose 1, it will be x raised to the 117, because that's 118 minus 1, 2, because I don't have y, I have 2 raised to the 1. So the term that I'm chasing is this entire thing. It is not just the x raised to the 117. So I have to do the 118 and choose 1. This is 118 factorial, 1 factorial, 118 minus 1 factorial. But I said, if I have an n choose 1, this is going to give me just n. So this is going to be equal to 118 multiplied by x raised to the 117 multiplied by 2. So I do need to multiply that 118 and that 2, and then that's my term. So I have 118 multiplied by 2, which is 236, x raised to the 117. This is my answer. It is not the entire expanding out. It is the answer that has the term which has x raised to the 117. So that one wasn't too bad. Now, my next one here, I want the one containing 7 over 2. What? Remember, I can write this as x raised to the 1/2 minus 3 raised to the 8. If I were to start expanding this out, I would have 8 choose 0, x raised to the 1/2 raised to the 8th power, negative 3 raised to the 0 power. That's my first term. This power to the power rule is going to be 8 over 2, which is 4. That's not the one I'm chasing. My next term is going to be 8 choose 1, x raised to the 1/2, raised to the 7, because that's 1 power less, negative 3 raised to the 1. This power to the power rule is 7 over 2. Oh, that's what I'm chasing. So this is the term that I want. 8 choose 1 is going to be just 8. I have negative 3, x raised to the 7/3, or 7/2, excuse me, 7/2. So the term that I'm chasing is negative 24, x raised to the 7 over 4. Now you're saying, what happens if I wanted the term, same exact problem, I'm still using this. Now notice my first two examples, I went to a specific term, right? Specific term was the second one in. What if I want x raised to the 5 over 2? Well, if I want x raised to the 5 over 2, I know I'm going to have 8 choose. This will be x raised to the 1/2 raised to the 5, negative 3. Now, whatever this exponent is plus this 5 needs to be 8. So I know that this has to be 3 because remember, numerically, these have to add up to 8, even though I can't truly add those exponents. And also notice, this choosing is always the exponent on my second term. So what I really have, if I want to have x raised to the 5/2 term, is 8 choose 3. So 8 factorial, 3 factorial, 8 minus 3 factorial, multiplied by x raised to the 5 over 2, multiplied by negative 3 raised to the 3rd. So 8 factorial, I'm going to bring it down to 5 factorial. So 8 multiplied by 7 multiplied by 6 multiplied by 5 factorial. I'm going to write 3 factorial is 3 multiplied by 2 multiplied by 1. 8 minus 3 is 5 factorial. That's why I went down to 5 factorial. This 2 times 3 cancels with that 6. So I have x to the 5/2. I have negative 3 raised to the 3rd power is negative 27. So I'm going to take 8, multiply it by 7, multiply it by the negative 27, and that's going to give me my coefficient. So I have 8 multiplied by 7, multiplied by negative 27, which gives me negative, do it in red, negative 1,512 x raised to the 5/2. If I wanted the term with 5/2, that's the answer. If I wanted the coefficient with the 5/2, only the numeric value is the coefficient. Okay, just wanted, because the two examples I did, it was the second term, and I really didn't have to do that much work, so I really wanted to show you what happens if it's not the second term. All right, last one. I want the constant. And you're thinking it's the last one, right? No. So let's start expanding this out a little bit. So I have 10 choose 0, x raised to the negative 1 raised to the 10, 2x to the 3rd raised to the 0. Now, this part is going to be 1, and this part is going to be x raised to the negative 10. So clearly, that is not the constant. So then my next one would be 10 choose 1. So x raised to the negative 1 raised to the 9th power. And then I have 2x to the 3rd. I don't know what happened there. Let me just erase that. Something weird happened there. So let me erase that weird thing that happened there. X raised to the 3rd raised to the 1 power. This is going to be x raised to the negative 9. Just this is x to the 3rd. I added these two exponents because I get to. Is going to be x raised to the negative 6. That's not the one I want. 10 choose 2. I have x raised to the negative 1 raised to the 8, 2x to the 3rd squared. This gives me x raised to the negative 8. And this one, notice I'm not paying attention to the 2 yet because I want to find the one that is constant. This is going to give me x raised to the 6th power. These two, because of like basis, is going to give me x raised to the negative 2. Still not the one I'm looking for. Okay. 10 choose 3. X raised to the negative 1 raised to the 7th. 2x to the 3rd raised to the 3rd power. This is going to give me x raised to the negative 7. This is going to give me x raised to the 9. And these two combined is going to give me x raised to the 2. Now what's going to happen? My next term is going to be 10 choose 4, x raised to the negative 1 raised to the 6th power, 2x to the 3rd. I don't know why it's doing that. 2x to the 3rd raised to the 4th power. Just this portion is going to give me x raised to the negative 6, and just this portion is x going to be raised to the 12. And so I end up with x raised to the 6th. And what's going to happen is that this is going to continue. So if they wanted the one that has a constant term, we don't have a constant term. There is no constant term in this expansion because my exponent went from x to the 10, or x raised to the negative 10, the exponent of negative 10, then the negative 4, or negative 6, then the negative 2, then the 2, then the 6, and the next one will be even higher. Because the next one would be even higher, I actually don't have a constant on this one. There is no constant on this one because you can see this one will have a power of negative 10. This one will have a power of negative 6. This one will have a power of negative 2. This one will have a power of 2. The next one will have a power of 6. And I can guarantee you that the next one is going to be, because it's going to be a power of 5, this is going to be a power of 10. So I don't have one. There isn't one. Because my powers are increasing on my x's. Now, let's do this again, where I have got x raised to the negative 1 plus 2x squared raised to the 10. Will I get a constant on this one? Well, again, I want to go ahead and start expanding out. 10 choose 0. X raised to the negative 1 to the 10 power. 2x squared raised to the 0. We know that this one is going to give me x raised to the negative 10. And this one's going to be x raised to the 0. Not helpful. Oh, and 2 raised to the 0 as well. My next term is going to be 10 choose 1. X raised to the negative negative 1 raised to the 9. 2x squared raised to the 1. This is going to give me x raised to the negative 9. X squared. Not worrying about this part, just worrying about these two. This gives me x raised to the negative 7. Okay. My next term would be 10 choose 2. X raised to the negative 1 raised to the 1 power less, which is 8. 2x squared squared. Again, this is going to be x raised to the negative 8. 2 squared, x raised to the 4th. These two combined is going to be 2 to the 2, 2 squared, and then it's going to be x raised to the negative 4. Oh, well, maybe I'll have a constant on this one. My next one is going to be 10 choose 3. X raised to the negative 1 raised to 7, 1 power less. 2x squared raised to the 3rd power. This gives me, again, I am not worried about the coefficient yet until I'm trying to find the constant. This is going to be x raised to the negative 7, 2 to the 3rd, x to the 6th. These two combine. X raised to the, this is 7, negative 7. This becomes negative 1, which is still not a constant. So let's do the next one. It's probably still not going to work. 10 choose 4, x raised to the negative 1 raised to the 6th power. And then I have 2x squared raised to the 4th power. these two, this gives me x raised to the negative 6. This gives me 2 raised to the 4th, x raised to the 8th. These combine to give me x squared. Now, they want the constant. Clearly, I don't have a constant yet again. But if they wanted the x squared term, the term that has x squared, then I would have found it. If they wanted the term that has x raised to the negative 1, I would have found it. This isn't going to have a constant either. So if they wanted either one of these, say they wanted the x raised to the negative 1 term, then I would do 10, choose 3. I needed this coefficient multiplier, 10 factorial, 3 factorial, 7 factorial. So 10, 9, 8, 7 factorial, 3, 2, 1, 7 factorial. These will cancel. 3 goes into 9 3 times. 2 goes into 8 4 times. So this is 120. This is the coefficient multiplier. I still need to do 2 to the third. So I still need to do 2 to the third multiplied by 120 multiplied by x raised to the negative 1. So I have 8 multiplied by 120, so the 960x raised to the negative 1. So if they wanted the term where I had x raised to the negative 1, I found it. I'm not going to have a constant on this one either. And that's it. If you have questions, bring them to class. We'll go over these. Otherwise, this is the binomial theorem, give or take.